In the first two parts, I looked at what controls and barriers are and how organizations specify, verify, and maintain them. But like ogres, barriers have layers. They depend on somebody recognizing an abnormal condition, interpreting information, making a decision or taking some sort of action, maintaining or testing equipment, or recovering control when something starts to fail. And probably pretty obvious, but human performance isn't separate to the barrier system. It's often part of the mechanisms through which the barrier works. That is, we're dealing with a socio-technical system. That raises the central question for part 3. How do we sufficiently specify human performance as a credible barrier? G'day everyone, welcome to Safe As. I'm Dr. Ben Hutchinson. Please like, comment, subscribe and share. First, there's so many studies and guides on these topics that I can't cover everything. But check out my blog. This compendium has over 100 studies on barriers and control approaches, among other articles. So the first source is McLeod's paper, Human Factors in Barrier Management: Hard Truths and Challenges. McLeod argues that organizations rely on people in two broad ways. People may perform control functions directly, as in they use or activate something, or they may ensure that physical, electronic, and engineer controls are installed, configured, and functional when needed. The difficulty is establishing whether that performance can reasonably be expected under the conditions in which the task occurs, and whether the wider control system remains robust when human reliability is lost or variable, which it always is. We're humans, we're not calculators. Now, a bow tie may show several clean control boxes. It's pretty mechanistic and inert, but each can contain unstated expectations, as in the right person will be available, the relevant information will be noticed or available when the person needs it. The situation will be interpreted correctly, or it matches the planned assumptions or procedure. The required action will be physically possible when it's needed. There will be enough time, and competing demands and pressures won't interfere with the task. McLeod distinguishes between intentions and expectations. Intentions are conditions the organization is responsible for putting in place, such as work arrangements, equipment, and the operating environment. Expectations are assumptions the analysis depend upon, but may not be under direct control, such as people being available, competent, fit for work, or aware of their role and not incentivized to weaken the barrier. So while human and organizational measures are important, they might not be strong enough to qualify as full barriers, as we discussed in prior episodes. The organizational climates, training, procedures, competency, supervision, and fitness for work arrangements may support reliable performance. Any one of them could be essential, but most can't independently stop the event pathway in and of itself. McLeod therefore argues that many of those things are better described as safeguards, protecting the real barrier. And think about it from this way. Procedures and plans, etc. are usually written from the perfect world scenario. They're almost always written as if the process will work first time, every time. Those assumptions make it easier to write a procedure and train people on it, but they don't, of course, reflect reality. And some final points from McLeod. He observes that top events in the bow ties are too frequently located to the right, as in the events they're trying to prevent are too close in time to the consequences, leaving less opportunities to prevent or block the propagation of that particular threat or failure pathway. Further, treating people as a threat obscures the opportunity to develop deeper understanding of the way people provide flexibility and adaptability, and hence contribute to positive safety capabilities. In McLeod's words, people are nearly always a positive element in complex socio-technical systems. Therefore, whenever possible, we should design our systems to ensure people have the necessary support, resources, and power to be as productive and adaptable as they can be. The second article from the Chartered Institute of Ergonomics and Human Factors develops this argument further. I'll call them the Chartered Institute. They provide an introduction of what not to do with a common bow tie that begins with human error as the threat, and then it inserts things like these on the screen as barriers, like procedures, training, communication, supervision, and competency. The Chartered Institute argues that This directs attention towards stopping an undefined human error instead of identifying the actual barriers and making them robust against the specific actions that could actually degrade them. It's actually a misdirection focusing on human error. Its preferred approach is to identify the actual initiating condition of that failure mechanism, identify the genuine barriers, describe the specific human failure that could degrade each barrier, as in the degradation, erosion or escalation factors, identify safeguards that reduce the likelihood of that degradation. These have also been called erosion or degradation controls, among other variations. This information sheet from the Western Australia government summarises this through 4 principles. Don't model generic human failure as the threat leading to the top event. Describe the specific failure affecting that particular barrier. Recognise that most human factor controls are safeguards rather than full barriers. And don't treat documents as controls. The control is the process followed or the completed action described in the document, but is not the document itself. That's consistent with the ICMM's critical control framework also. So in other words, instead of writing operator error, describe exactly how the operator didn't detect the alarm, the control setting was entered incorrectly, the isolation wasn't confirmed, or the inspection failed to identify the X degraded condition. Now, the failure is linked to a specific barrier function that can be examined and improved. As argued by others, human error isn't the conclusion, it's the start. The point at which our investigations and learning should become more specific. One caveat though, the Chartered Institute does allow human error to appear as a type of threat, but only at the lower level of analysis. You pick the main bow tie, which is what they call level 0, pick the barrier you're worried about, then drop down a level where the failure of that specific barrier becomes the top event. At that level, a specific human error, not literally the term human error, actually articulate what type of human performance we're talking about. And there it's legitimately a threat and you map the safeguards against it. So it's those degradation or escalation controls. Going back to that Western Australia guidance document, now it defines barriers as primary controls that are specific, independent, effective on their own, and auditable through performance standards. So we already covered that in the previous episodes. Now zooming into human performance, we can look at the human factor controls that usually safeguards because they often can't meet those conditions independently. Safeguards is in something which has an important role in implementing, supporting or maintaining barriers, but doesn't meet the minimum conditions to be considered as a barrier on its own. On a similar note, these are referred to as erosion controls and support activities in the ICMM guide, and they have other names. For example, an alarm system requiring a person to activate an emergency response may qualify as a combined human and technical barrier. But in contrast, cross-checking and training and competency, they're listed as safeguards because they don't meet all those conditions for a barrier or a control. They support the barrier, but don't independently perform its function. As noted in episode 1 and later in 4, is this thing called the fallacy of social redundancy. Human actions likely aren't as independent as we assume them to be. An example from the Chartered Institute relates to operator independence. The checkers, people who check something, like a torque setting, often fail to see the errors because they trust the doers, meaning the intended independent check isn't so independent. Procedures, training and supervision are all important, but none of those elements automatically constitute an independent barrier. The analysis should begin with the safety critical task and ask something like, what must actually happen to prevent, control or mitigate the event? Only then should we decide whether the human action is a type of barrier or one element of it a barrier element, or is it a safeguard, a verification activity, or part of recovery. A lot of that will probably depend on the type of organization and its worldviews and which barrier or control framework you're using. The Chartered Institute also has a helpful table covering the features of an effective versus an ineffective human barrier. What doesn't make for a good human barrier is if the task is vague, or it's unclear what would trigger it or how you would know if it even worked. Nobody specific owns it. It overly relies on complex judgment, especially where safety and production pull in opposite directions. It's only been designed for that perfect world scenario, or it assumes people will be fully compliant at their best while busy and stressed. It relies on constant situational awareness. Now, I'm not going into the criticisms of situational awareness here. It needs people with different objectives to coordinate perfectly. It makes no allowance for the unexpected, what we'd call brittleness from the resilience engineering perspective. Or it depends on someone spotting an early signal that's weak ambiguous, or easily missed. In contrast, they provide examples of what makes for a good barrier. Mostly the opposite of those ones I just covered, but as in a clear, specific task, a named owner, realistic expectations. The person can detect the situation, work out what to do it in the time and with the gear available, and get feedback that it worked. Strong triggering signals, and ideally, limited reliance on real-time safety versus production trade-offs. Many of these issues, at least in theory, weaken or maybe even disappear when you clearly assess and articulate the human performance standards. A central idea in some of the barrier and control frameworks is the detect, decide, and act cycle. Active barriers often depend on three linked functions: detect the condition, decide what response is required, and to control it. If any function is missing, the control may only be one barrier element rather than a complete barrier system. Like with an alarm, the alarm may detect and communicate an abnormal condition, but the complete barrier system may also require someone to interpret the alarm and activate a shutdown. Useful prompts therefore to ask for detect: what condition must be recognized? By a human, I mean. What cue provides the information? Is that cue visible and distinctive? Can failure of the detection system itself be recognized? For decide, what interpretation is required? Is the correct response unambiguous? Is a complex judgment involved? Could the person face a trade-off between safety and production? For act, what action is required? Who performs it? How quickly must it begin and finish? What equipment, communication, and authority are required? We can also add further assurance questions like, how is successful action confirmed? If any part fails, how will the failure be detected and recovered before serious consequences occur? Levinson's work adds a useful point to detect, decide, and act. People don't necessarily act on the system's actual state. They act on their own mental model, their current understanding of what's happening. And this shapes how we make sense of the world. Now, of course, that model can be wrong from the outset, or it can become outdated through missing, incorrect, or delayed feedback. A person may therefore respond logically to a situation that just doesn't exist in reality. For example, believing an isolation is complete, an alarm is active, or an earlier step has been performed or double-checked. So for any human-dependent barrier, we probably should ask, what must the person believe for this action to make sense? And what feedback reveals when that belief is wrong? The barrier must support not only detection and action, but an accurate, continuously updated understanding of the system state. Easier said than done. Technical barriers normally have performance requirements. Now, the Chartered Institute argues that human-dependent barriers need that same level of discipline. The Western Australia information sheet summarises 6 required characteristics. First, define the actor, object, and goal, as in, who acts? What do they act upon? What safe condition must be achieved? Second, identify everyone involved. Who detects, decides, and acts? Who supplies information, coordinates the response, or confirms completion? Third, define competence. What task-specific knowledge and capability are required? Fourth, define the timing, as in, how quickly must the action begin? How quickly must it be completed? Are those times compatible with the speed at which the threat develops? Can people actually recognize and make sense of those threats quickly enough to actually develop a plan and perform the plan? Fifth, define successful performance. What observable or measurable result demonstrates that the barrier function has been delivered? 6, record critical operating assumptions. What assumptions about staffing, equipment, information, and operating arrangements must remain true for the barrier to function as expected? For example, stating something like a competent operator will respond appropriately isn't a performance standard because it leaves things like the actions, the triggers, the timing, etc. unstated. This is where we set people up to fail. The Chartered Institute highlight the Deepwater Horizon or Macondo accident. The barrier logics assumed the crew would detect gas entering the riser, quickly judge that it needed diverting overboard, and complete the correct multi-step diversion sequence, all in the tiny window available. The US Chemical Safety Board, or CSB, found the cognitive complexity and time pressure made that unrealistic for any crew, and that commercial and regulatory pressures may have pointed them the other way. So they weren't set up to succeed because they weren't realistic, accurate, calibrated human performance expectations. The Chartered Institute also helpfully describes the conditions that need to be in place for people to be successful. Like, number 1, match the barrier to the job. Expecting highly qualified senior people, the ones you hired for judgment and problem solving, mind you, to blindly follow procedures probably isn't a robust plan. If we hire them to use judgment, set them up to use their judgment. 2, build in natural incentives. Like the person using it, a barrier or procedure, whatever, gets some benefits from doing it properly rather than another bureaucratic burden. And as the universe shows us, there shouldn't be an easier way to do the task than the way you've designed and implemented. If there is, people will find it. Not always literally possible, of course, but a nice design philosophy, I think. And as it's stated in these safety 2 and HOP areas, make it as easy as possible to do the expected or right thing and as hard as possible for the incorrect thing. 3, design for the least capable person who might hold the role or do the task, including on a temporary basis, on the worst realistic day. Not your best operator in ideal conditions, that perfect world setting. Probably can't do that for every control and process, but if it's that important to you, if it has to go right first time every time, then you probably do need that level of granularity. 4, close the loop. Feedback on how well the barrier has performed should fall out of the normal job, not depend on a separate audit. Provide ready, real-time, accessible feedback. Next, we're unpacking the IOGP report 642, titled Learning from Normal Work. In short, this guide looks at whether our performance standards can be achieved under the conditions in which the work is actually done. It's fair to say that much of how organizations are currently geared and designed to learn is centered around incidents. But those events represent such a small proportion of the total work. Everyday tasks also contain intel around constraints, adaptations, risk pathways, and potential control weaknesses that remain largely invisible if we only investigate adverse outcomes, which are typically fairly rare. Now, clarification on terminology. In this section, constraints means the practical limitations shaping work like time, staffing, tools, access, or information. This is different from a system safety constraint, as in a condition that must be maintained to keep the system in a safe state. Now, operational constraints can make it harder or sometimes impossible for people to enforce the intended safety constraint. This report defines normal work to include both routine tasks, the ways people adapt to varied challenges so that operations are completed successfully. It's also referred to as daily work or everyday work, among other terms, like weather, stuck valves, missing tools, inexperienced colleagues, unexpected readings, and unplanned personnel in the work area can all change what a familiar task requires. That's all normal stuff. And this reveals an important consideration. An incident-free outcome doesn't necessarily demonstrate that the barrier worked to design or the risks were under control. Things are argued to go wrong for the same reasons they go right. Success and failure in this logic aren't opposites with a different cause. They come out of the same everyday performance variability, the same adaptations people make to get the job done. The report examines how finding broken part mindsets works well for equipment, but doesn't hold well for people in complex operating environments. And if we only study the rare failures, we miss the variability happening on every successful job. And this is where we can unearth error traps. For one, the task may have succeeded because somebody compensated for missing equipment, poor information, an impractical procedure, changing conditions, or another weakened control. An error trap is any condition that makes a mistake more likely. It's a feature of the work, context, or design, not the worker. For example, gauges mounted on the opposite side of a pump from the controls, so the operator can't see the reading while working. A valve you can only reach by squeezing between the generator and a beam, one-handed. A procedure listing pressure and PSI, while the gauge reads in MPa, as in leaving the operator to convert on the fly, if they even realize that. None of those are failures of attention or attitude. They're features of the environment that increase the odds of error. One apt warning from this guide: when you're identifying error traps, don't confuse them with behaviors, as in selected the wrong tool or skipped a step isn't an error trap. It's the thing you're trying to explain. Don't stop at cognitive states either, as in wasn't paying attention or wasn't aware, because that doesn't tell you about the mechanisms that produce them and try to limit or avoid judgmental labels like complacency or overconfidence. They just relabel blame and ignore the context. Verification should examine how success was achieved, not merely whether harm was absent. This is the gap between work as imagined and work as done. The plan, procedure, the bow tie, that's all work as imagined. The idealized version, the perfect world. Work is done is what people actually do once we factor in weather and missing tools, time pressure, and everything else that happens in real normal daily work. As the report puts it, accidents are unexpected combinations of normal variability and the adaptations people make to local constraints. Hence, a mechanistic model like a barrier framework really only ever shows you work as imagined. The IAGP describes factors that shape work through terms including constraints, error traps, and performance shaping factors. These might involve a range of factors like time and staffing, tools and equipment, information procedures, task complexity, equipment design, production pressure, budgets, and more. On this, workarounds might help someone overcome a limitation, bypass an obstacle, or substitute for a missing resource. Workarounds are probably far more common in your organization than you realize. Healthcare data suggests that at least 10% of a nurse or clinician's shift is spent working around established process. Amy Edmondson in the Fearless organization makes an apt remark about why workarounds are so difficult to fully eliminate. In her words, the problem with workarounds is that they work. They accomplish the immediate goal, but they don't diagnose or fix the problem that triggered them. And in getting the job done, they quietly create new ones. Amy notes that workarounds often shift risk or issues elsewhere, like with one ward short of linen, so a nurse grabs some linen from another ward. That fixes that nurse's immediate issue, but leaves the core issue in the system and takes resources away from that other ward. And potentially more importantly, workarounds silence signals for improvement. The problem that triggered it was a small sign that something in the system needs changing. By bypassing the signal, we lose the opportunity to identify it and resolve it. So instead of just asking, why didn't they follow the procedure? Try asking, what problem was the adaptation solving? Then maybe try asking something like, did it preserve or weaken the barrier function? Is it used routinely? What new dependency or risk did it introduce? Could the useful part of that workaround be incorporated formally? Or should the underlying constraint be removed? A workaround affecting a critical control or a barrier is evidence about the design and usability of the control system, and not merely evidence of non-compliance. As Decker argued, a human error problem is an organizational problem, and at least as complex as the organization that helped create it. The IAGP guide discusses a practical tool called Walkthrough Talkthrough. An experienced person demonstrates and discusses the task where it's performed. The task is considered step by step, asking things like, what could go wrong? What could the consequences be? What makes this step difficult? What increases the chance of error? What might confuse someone unfamiliar with the task? What improvement could reduce those conditions? Now, note, this isn't behavioral observation, but understanding the task and the conditions influencing performance every day. Walkthrough Talkthrough is said to be most suitable for establishing activities with reasonably sequential steps. The IAGP notes that it may be less suited to complex work across several functions or to activities involving continuous dynamic adaptation. In barrier terms, a walkthrough talkthrough takes the control out of the bow tie and tests whether it makes sense in the workplace in that context with the constraints people face or could face. Also, there are several related approaches I can't properly cover here, but they offer useful ways to strengthen a barrier system. So here's my rushed and lazy attempt to shoehorn all those things in. First is safety critical task analysis, which breaks a high consequence task into stages and examines what could go wrong at each stage, the consequences, the error mechanisms involved, and the conditions making error more likely. It can expose weaknesses hidden behind a statement such as operator follows a procedure. There's also cognitive task analysis and cognitive work analysis, which are a class of different techniques for exploring what people think about what they do and why. They're really cool. You should check them out. We also have learning teams, which take a broader view. They bring people together who influence or perform the work to understand how it normally happens, including constraints, to learn about adaptations and dependencies across functions. Learning teams might explore things like planning, maintenance, handover, procurement, or decisions made elsewhere. But all of these methods and tools that I've discussed tend to be more complementary rather than interchangeable or in conflict. Finally, Tony Mashara, Ron Harris, and Jim Marinis propose focusing on critical steps. They define a critical step as a human action that will trigger immediate, irreversible, and intolerable harm if that action or a preceding action is performed incorrectly. This process directs attention away from just looking at important steps towards the moment where control can be lost and recovery is no longer available, as in exchange of large energy or whatnot. The authors also identify risk-important actions, preceding actions that establish the conditions under which the critical step will be later performed. Packing a parachute precedes the irreversible act of leaving the aircraft. So that's your critical step. The packing can still be checked and corrected before the person jumps out. But once the person jumps, those earlier conditions determine whether the system works. A critical step is stepping out of the airplane. You can't step back in. It's irreversible. And they know that you don't actually need a parachute to skydive anyway, unless you want to do it twice. Now, learning from daily work provides both reactive and proactive learning, like intel about barrier systems. Incidents and near misses provide another, albeit limited, test of the barrier. Investigation should, in part, try reconstructing how the task should have been completed, as in testing our assumptions, workers imagine, etc. How the task is normally completed. How is it completed on the other day and on this day? And what does good look like? What's good recognized practice? Though, being a little careful of counterfactual reasoning. It's good for what ifs and risk assessments and proactive thinking, not so good for trying to explain what has already happened. Investigation should examine things like the cues and information that was available, what the person understood at the time, whether required action was achievable, which safeguards worked, failed, or were absent, and whether the error could have been detected and recovered. Even try the substitution test. Would have it similarly affected other people if you substituted them? If the finding is simply human error, fatigue, poor procedure, or lack of competence, your examination is probably incomplete. Send it back. Those descriptions may identify the failure or its immediate conditions, but don't explain how the barrier system allowed those conditions to defeat it. As highlighted elsewhere, like Harm's ring doll, you can explore barrier functionality with specific prompts, including, was the barrier function in place and did it function satisfactorily? Was the barrier function working to some extent, but not completely? Did the barrier perform and not perform as expected at all? Was the barrier system or elements not implemented, or was it only partially implemented? And more, there's variations of these. So what can we make of the findings? I covered a lot again. In all, a credible human-dependent barrier needs more than a procedure and a trained person. It needs more than hopes and dreams and chocolate-flowing rivers and gumdrop smiles. It requires a clear safety function, appropriate classification as a barrier, element, control, or safeguard, whatever, a specified actor, action, and safe state, a complete detect, decide, act, cycle, which may not always be possible though, realistic timing and operating assumptions, information, competence, tools and equipment supporting the task, feedback confirming success, opportunities to detect and recover from failure, and understanding of shared dependencies, and evidence from everyday work, near misses and incidents and every other stream of intel that inform whether the complete system can be formed as required. The human barrier is a safety function delivered through the person, task, information, equipment, available time, feedback, and the wider work system, the socio-technical system. We need to set people up to succeed with realistic and tested expectations, resources, feedback mechanisms, and the power to act, not simply assumptions and best wishes. To decide whether it deserves barrier status, we need to specify the function, examine it during everyday work, learn from successful adaptations and failures, and verify that it remains achievable under real operating conditions. Part 4 will take the next step and ask what barrier models still miss when the work is variable, adaptive, and never quite identical to the plan. It's a critical perspective based on the Safety 2 principles. That's it on Safe As. Please like, comment, subscribe, and share, and link in comments to support the channel.